What do you notice that is different about this question? Yep. What else? Do you think you could do it? Try. The base is x. That's different from everything else in this unit. Good. What else? What else? Do you see an x in the base anywhere else? In the exponent as well. And that is troublesome. So we've certainly not seen this before. We did a lot of work where there's an x in the base, but not both in the base and the exponent. So this is not something that any of our derivative rules will work for, any of the ways that we've done it in the past. So what can we do? Why would that help? Very, very good. Logs are the way that we can take an exponent out of the exponent and bring it kind of down to the same level. Logs is all about comparing exponents, right? So raising the argument of a log is the same as multiplying by the log. Like, that's our property, okay? But it's kind of like back in MHF when we did those problems involving logarithms. So we talked about earthquakes and loudness. But the point is those scales are logarithmic. So when you go from a 5 to a 6 on the Richter scale and then a 6 to a 7, that's not the same increase. That's an increase 10 times more intense, a 6 to a 7 compared to a 5 to a 6, right? Because the scale is not a linear scale. We talked about this. And so logs is the idea of comparing exponents. One way of thinking about it is if you're working with really, really big numbers or really, really small numbers, you may not really care about whether it's 1.16 or 1.36. What you care about is it 1.16 times 10 to the 32 and 1.36 times 10 to the 40. That's all you care about. All the other numbers you don't care about, right? You care about the exponent on the 10 kind of thing. So that's what logarithms are useful for. That's what they do. In this case, what we're going to do is take the log of both sides. What do you think base log we should use when we take a derivative that's going to make things easier? Say it again. Why 10? Okay, good. What would be an even easier base if we're going to do derivatives? E, because then we don't have to worry about the constant. But this would work for any base, of course. So, in fact, we're going to take the log base E, which we write ln of y equals the ln of x to the 3x squared. Now I'm going to take the exponent, the 3x squared, out. And usually I'm going to skip that first step and kind of go straight to this, just FYI. And now we can take the derivative, but it's implicit differentiation because I have the ln of y, so I have to take the derivative of that. What do you think the derivative of the ln of y is with respect to x? dy by dx, and then what was the other part that you said? Ln y? Close. 1 over y, yeah. Make sure we don't get, like, e to the x is e to the x, so it would be e to the y if it was e to the y. But ln of y is 1 over y. Good. Okay, and then we have product rule here. So derivative of the first thing is 6x times the second thing plus the first thing times the derivative of the second thing, which is 1 over x. So I could just write it like that, over x, right? Times 1 over x, like that. But since I've got this part, I can just put over x. However you like to think about it is fine. Now I'm going to bring the y over. So I'll multiply both sides by y and do a little bit of simplifying. 6x ln x I can't simplify, but 3x squared over x I can. And then the rule for this process for us, this again is not like a math rule. This is just the way that we're going to do this and practice it. Something we haven't really done before, but I'm going to replace the y. What should I replace it with? Jason?
X to the 3x.
Yeah. Why would you do this? Yeah, good. If you want it written back in terms of x for some reason, you don't want it to be in terms of y, this might be a worthwhile thing to do. We didn't do this in the past, partially just because we didn't, partially because we had a lot of y's, and that would be a bit of a disaster, maybe subbing a complicated expression into a bunch of places in an even more complicated expression, right? So all those other ones we were doing, that it wouldn't, if you look back, it probably wouldn't have made as much sense. But you could have all the implicit differentiation we've done, well, maybe not all actually, that's not true, but some of them had expressions for y, some of them didn't, that's why you couldn't, I suppose, but some of them may have had expressions for y, we just didn't. But this one does, and it makes sense. But I'm going to leave it like that. I'm not going to actually expand it through. Questions? So that's the process. Take the log or the log of both sides, but base e is a good choice. And then differentiate with respect to x. Solve for dy by dx, and then resub in for y, so that we have an expression in terms of x, because we can. Y equals, this should be cos x. Y equals x to the cos x. When you have x in the base and in the exponent, this is how you have to differentiate. So for example, on the test, there might be a question that says differentiate each of the following. If one of them is like this, you need to know that's how you do it. Okay, that's part of this, but it's pretty clear, it's pretty straightforward. You do this a few times, you kind of remember today, and you're like, it sticks out pretty well. And if you tried to do it a different way, it wouldn't work. So we've got ln y equals, this is where I could take the exponent down right away, cos x ln of the base, which is x. Okay, you go ahead and try. While you're doing that, I'm actually going to write this down. You can if you want to, but you probably won't remember it. Logarithmic differentiation. If you didn't see the title, that's what we call this. Logarithmic differentiation, it just means we're like it wasn't a logarithmic function, but we're using logs to simplify it and put it in a way that we can differentiate. Product law again, what's the derivative of cosine of x? Have you forgotten it already? Nice. Don't forget the negative sine x times the second thing plus the first thing times the derivative of the second thing, and the derivative of ln x again is just x. That's not always going to be that simple, but this time it is. This is, oh yeah, this is one of those good things in like grade 11 when you start learning about some of this stuff and doing identities and stuff. Oh, can I do this? It's just cos. Oh my gosh, please don't ever do that. Why does that not make sense? I'll let you think about it, but yeah, you definitely can't simplify those, right? Okay, and then replace the y, which was x cos x we okay? Questions? Okay, there's another one for you to try. They usually work out to relatively simple product law questions, I would say, compared to some of the stuff that we've done. So shouldn't be too problematic. Whoops. Skip this step. Looks like people got this far. Derivative of the first thing is 4x cubed, so the derivative of that is 12x squared times the ln, the whole second thing, which is the ln of 3x minus 4, plus first thing times the derivative of the second thing. So what's the derivative of the ln of something? One over a times the derivative of a. So 1 over the whole ln argument. So I can put that whole thing in the denominator there, times the derivative. And in this case, we have something, the last couple examples was just an x, so it was times 1, so we didn't bother with it. But this time it's times the derivative of 3x minus 4, which is just 3. Oops. So 3 times 4 is 12, so I've got 12x cubed over 3x minus 4. And then replace. And it looks like I could factor that second part. There's a nice 12x squared that I can factor up, but we don't need to worry about that, bother with that. Any questions? We've got a couple more examples, that's all. All right.
Oh.
How many people got this far so far? So the derivative of the first thing is 2 times the ln and square root of x plus 2x, the first thing, times the derivative of the second thing. So 1 over the argument of the ln times the derivative of what's inside. Remember when I said a few days ago, boy, we've taken this derivative a lot of times. We kind of know it by now. 1/2 x to the negative 1/2 x. Just put your pencil down and watch for a minute. How am I going to clean this up? So I'm going to get 2 ln root x plus, well, I see a 2 up here and I see a 2 down here, so those are going to be gone. And this is 1 over the square root of x, and this is 1 over the square root of x. 1 over the square root of x times 1 over the square root of x is going to give you what? 1 over x. So, and the 2's are gone, so do I just get 1 over, oh, sorry, there's still an x there. Don't forget that. I almost missed that. So there's an x over x. So that's going to be 1. So I get dy by dx equals square root of x to the 2x times 2 ln root x plus 1. But hold on a minute here. What's another way of writing the square root of x to the 2x? Think about your exponent properties. Ah, x to the x. How? Why is it x to the x? So this is like the square root of x squared all to the x. Because if I'm multiplying exponents, that's a power to a power. So this is y equals x to the x. So this is the ln of y equals x ln x. 1 over y dy by dx equals 1, right, the square root of x, which is 1, times the ln of x, so ln x, plus x times the square root of ln x, which is over x. So this dy by dx equals y times ln x plus 1, which doesn't quite look like that second part, or the first one that we did. So what's wrong? Just because they don't look the same doesn't mean they aren't the same, but what do you think? Can you resolve that? Yeah, so what can I do with it? 2 ln root x is the same as ln of root x all squared, which is just the ln of x. So this is actually ln x. It's not to say that you would know to simplify it that far. It's not to say that you have to do it like this. This way on the right is a lot easier, I would say, or a little bit easier, I would say. You don't have to notice that. You don't have to do that. They're nice things to notice. It's the kind of thing that makes math easier when you start to notice those relationships more and more and more on your own. But it's also just kind of fun to remind ourselves about how these things can be solved and simplified in different ways, and how these properties always work out, and how, you know, we can use these properties in unexpected ways maybe. Everybody get that down okay? All right, one more. Oh my goodness. This one's just for funsies. So I don't think we've ever done anything quite this complicated. What do you think about this one? If you had to do this, what would you do? Not do it? Skip it? I'll take the 5-mark loss on the test. If you had to do it, what would you do? Well, it's quotient rule. So you'd have to do the derivative of the top times the bottom minus the derivative of the bottom times the top. But when I took the derivative of the top, it's product rule. And when I took the derivative of the bottom, it's product rule. Oh my goodness. So I think we have about 20 minutes left of class, so you can try to get this done by the end of class. Or do you want me to show you an easier way? Should we look at an easier way? Is there a reason why we're doing this question today? What if I take the ln of both sides? What's going to happen? Well, let's do it and look. We don't have exponents here, right? So we're not like pulling things out front like we did last time. So it's just the ln of this whole big disaster. 3x plus 7 to the 4 times the square root of 9 minus x squared over e to the 4x cubed times the square root of x squared plus 1. Now what do we think about this? Think about your log properties. Yep. Absolutely. So in other words, this ln of a times b equals ln of a plus ln of b, or log, and ln of a over b equals ln a minus ln b. Can we use that property? We sure can. Let's do it. So we've got ln of y equals, and this is how it's going to look, ln of the first thing, plus 7. Oh, you know what? I did something wrong here. I'll fix it in a second. This 3 is supposed to be, I believe, yes, it's supposed to be in the square root. Wouldn't really matter. I mean, it would change our answer a little bit, but the 3 was supposed to be in the square root. I kept doing that. Okay, plus ln of the square root of 9 minus x squared. And then I can just subtract the other 2. So I don't have to do it in 2 steps, but you can think of it however you want to do it. Ln of e to the 4x minus ln of the cube root of x squared plus 1. Do you think that's going to be easier? I can tidy this up a little bit more before I even start. You could do it as is, I think, but I think this is easier. I'm going to pull this exponent down, so this is 4 ln 3x plus 7. What's this next part? Yes. Very nice. And now I don't have to deal with any square roots. Isn't that nice? I don't have the negative exponent part subtracting and getting a negative 1/2. Like, that's a really good thing to do. It's really useful. What's ln of e to the 4x? Can I simplify that at all? I can bring the 4x out front. What's the ln of e? E is a number, so ln of e is a constant. One of our favorite constants. Yeah, because ln of e is 1. That's a nice constant to work out to. So it's just 4x. Very nice. And then this part is a cube root of such and such, so it's minus 1 over 3 ln of x, squared plus 1. Now I think we're ready to go. Now I'm going to let you try this. And we're done. Any questions? Think about how bad it would have been if we had done it the way we originally thought we were going to have to do it. Quotient rule and product rules. Now, if I were actually to fill in these 2 square brackets at the bottom, this is going to be that mess that we started with. And then this is another mess. And so if I wanted to expand those at that point, like that would be, again, a disaster. Yeah, now we take the second derivative. So, you know, like, I mean, in that case, you're not getting out of the trouble and you're going to use a computer or something, or I don't know why you would ever be taking the derivative of a function like that anyway. I don't know that that function would actually represent anything. But it's interesting to practice it algebraically, and it just shows you the point is, so at the beginning of this period, we talked about how if you have x in the base and x in the exponent, you must use logarithmic differentiation. If you have a very complex product quotient rule, something like that, it might be easier to do it with logarithmic differentiation. It might be easier to take the log of both sides, and then that depends on maybe what you're doing with it next. Okay? Any questions? Okay, here's your practice, page 324, 1 to 4.